Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Welcome to Pastor Victor's Academy. I'm glad you are watching my video. I can assure you that you'll learn a lot in this video by the time you are done watching. In this lesson, I'll be talking about limits. Please pay attention as we continue. The limit of a function describes the value that a function approaches as the input value gets closer to a certain point from the left and from the right. Take, for instance, we have a function f of x equal to 2x. Now, as x gets closer to 2, f of x will be getting closer to 4. So it's not just about integers. It's just a number that, or a value that a function tends to as the input variable, that in this case we have x, tends to a certain number or gets closer to a certain point. Now look at the second example. As x approaches 0.21, f of x approaches 0.42. That's it. 2 times 0.21 will give us 0.42. So that's what the limit of a function is. Take note, I said when the input variable or input value gets closer to a certain point from the left and from the right. Now for us to understand the concept of limits very well, I'll be defining two things here. The first one is the right hand limit, and the second one is the left hand limit. So, what's the right hand limit about? The right hand limit of a function describes the value that a function approaches as the input value gets closer to a point from the right hand side. Because the fact that you're approaching a point doesn't mean that if you're approaching from the right, you get the same value you are supposed to get when you're approaching from the left. So when you're approaching a point from the right, that means the right hand limit is the value the function tends to as you get closer to that point from the right hand side. That's what we'll have here. Here we'll have a point C, and that's 2. We'll have positive infinity, we'll have negative infinity. Here is x. So this is a number line for x. When we're approaching C from the right, that means from this side. When we're approaching C from the left, that means we are moving from this side. So in that case, the left-hand limit of a function describes the value that a function approaches as the input value gets closer to a point from the left-hand side. So that's what right-hand limit and left-hand limit is about. This is how we express it mathematically. Limit of a function of x as x approaches c plus. So this is the right hand limit. So we use the plus to indicate that x is approaching c from the right is equal to, let's say, j. Then for the left hand limit, limit of function of x as x approaches c from the left is equal to, let's say, k. So in this case, c is 2. As we approach c from the right, let's say the answer is j. As we approach c from the left, let's say the answer is k. So in that case, the limit of a function exists if and only if the right hand limit and left hand limit both exist and are equal. So look at this. Here we have the right hand limit, we have the left hand limit. We say let the right hand limit be j, let the left hand limit be k. So if we have a value for j and a value for k, and j is equal to k, which is equal to L, it means that the limit of the function as x approaches c, you will notice that I didn't use plus or minus because from the definition we said that the limit approaches from both sides. So as x approaches c, the limit of the function is equal to L. Now look at this, f of x is equal to 2x. Let's see what happens as x approaches 2. So we'll have 2 here. We'll approach from the right, we'll approach from the left, and see what happens. Approaching from the right, we'll be having 2 times 2.01, that gives us 4.02. 2 times 2.001, that gives us 4.002. Now let's approach c from the left. So we're having 1.99, 1.999. Now 2 times 1.99 will be giving us 3.98. 2 times 1.999 will be giving us 3.998. So you can see as we keep going closer to 2, our answer tends to 4. Then that's from the left. As we keep going closer to 2 from the right, our answer also tends to 4 because this is greater than this. Here we'll have 4.002. Here we'll have 4.02. So coming from the right, you see that the function approaches 4. That means limit from the right hand side is equal to limit from the left hand side. So we have it like this: limit of function of x as x approaches c plus is equal to limit of f of x as x approaches c minus, which is equal to L. If this condition holds, then we can say that the limit of the function of x as x approaches c is equal to L. Otherwise, the function has no limit as x approaches c. So if this condition does not hold, it means that the function has no limit. But when this condition holds, it means that the function has limit. So I want us to try some examples. You have limit of 2x plus 1 as x approaches 2. Now normally you know that when we have 2x plus 1, what do? We put 2 there. That gives us 4 plus 1, which is equal to 5. 2 into 2 plus 1 equal to 5. But now I want to see, as we go close to 2 from the left hand side and from the right hand side, let's see what happens to the function. So I have 2 here. I'm approaching from the right, and I'm also approaching from the left. So here is x, and here is our function, 2x plus 1. So we have 1.9, 1.99, 1.999. So you can see that this value is bigger than this is bigger than this. So what happens to the function? 2x plus 1 is equal to 4.8. Now, when we go further, we have 4.98. We'll go further again, we have 4.998. So you can see that the value is tending towards what? 5. Then let's approach from the right. This value is bigger than this value. This value is bigger than this value. So coming from the right, we have 5.2, then 5.02, 5.002. You can see that the function is decreasing and coming to 5 as we are coming from the right hand side. So the limit is also equal to 5. In that case, the limit of the function as x tends to 2 is equal to 5. Why? The left side limit and the right side limit are both equal, and that is what? 5. So that's what we would have achieved just by substituting for x in this function, and that will give us what? 5. Let's look at the next example. Find the limit of x squared minus 1 over x minus 1 as x tends to 1. Now when we substitute for x, we'll be having 1 squared minus 1 over 1 minus 1. That will be giving us 0 over 0. This is intermediate. This is not a number. So we need to know what is the limit as x tends to 1. That means we'll have to test it from the right hand side and from the left hand side. So we'll have the number 1, then from the left hand side, then from the right hand side. Here is x, here is our function. We'll have 0.9, 0.99, 0.999. So you can pick a value very close to 1, but not 1. Then from the right hand side, we have 1.001, 1.01, 1.1, 1.2, and the rest. So for 0.9, we'll have 1.9. For 0.99, we'll have 1.99. For 0.999, we'll have 1.999. So you can see that this is approximately 2. Then when you are coming from the right, you have 2.1, 2.01, 2.001. And this is also approximately 2. So it means that the left-hand side limit is equal to 2, and that's equal to the right-hand side limit. That means the limit of this function as x tends to 1 is equal to 2. Now, when we plot the graph of this function, you will notice that it is a straight line that cuts the y-axis at 1. Then it has a gap at x equal to 1. The gap here means that at x equal to 1, the function is undefined. So the fact that a function has a limit at a particular point doesn't mean that that function is defined at that point. So at this point, the function is undefined, but the limit is 2. So you can see that we'll have a gap. After this gap, the line continues. So at 1, the limit of the function is equal to 2. We would have achieved this by just factorizing. Now we know that x squared minus 1 over x minus 1 is the same thing as x plus 1 into x minus 1 over x minus 1. So this will cancel this. We are left with x plus 1. Then at x equal to 1, we'll be having 1 plus 1 equal to 2. So you can see that the answer gave us 2 at 1. But using the original function, we are having 0 over 0. So what it means is that the function is undefined when x is equal to 1, but has a limit which is 2 when x is equal to 1. Let's touch other two examples before we go on. Okay, we want to calculate the limit of sin x over x as x approaches 0. So here we have x, and here we have our function sin x over x. We have when x is equal to minus 2 degree, then here is our result, minus 0.1 degree and 0.1 degree. I remember when I was still in first year, I would just do sin x over x, not knowing that I have to convert x to radians for the denominator. So here x will be in degrees, and here x will be in radians. If you use the same value, let's say minus 2 here and here, you will get a wrong answer. So while you use minus 2 for sine x, you use the equivalent, that's in radians, for x. And to convert to radians, you just say theta over 360 times 2 pi. That will give you the equivalent in radians. So minus 2 degrees equal to minus 0.0349. That's approximately. So sin x over x is 0.999986. So you can see that this value is almost equal to 1. Then let's take a smaller value, or let's take a value closer to 0. We're having minus 0.1 degree. Use this formula, convert to radians. It is equivalent to minus 0.001745. Then punch sine minus 0.1 degree divided by this value. You'll be getting 1.000188. That's for the negative side. Then let's pick a value on the right hand side, that's 0.1. So we are having 0.001745. When punch sin x over x, you'll be having 1.000188. You can see that the left side limit and the right side limit, that's approaching from the right and approaching from the left, is approximately equal to 1. So in that case, the limit of sin x over x as x approaches 0 is equal to 1. So if you pick values very close to 0 from the right side and from the left side, you'll be getting almost 1. That's values very, very close to 1, but will not give you 1. So in that case, we say that the limit is equal to 1. Now, we would have done this just by differentiating the numerator and the denominator. When you differentiate sin x, you have cos x. When you differentiate x, you have 1. Then substitute for x at 0, cos 0 is equal to 1. So you can see we got the same 1 we got. Let's look at the next example. Limit of 1 over x as x approaches 0. If you just put 1 over 0, you'll be having what? Undefined. So we want to know, does this function has a limit? Is there a value it tends to as x approaches 0? And to confirm, we have to approach from the left and from the right. So we have x, then we have 1 over x. So we have minus 0.1, then minus 0.01, then minus 0.001. So this value is closer to 0, then this is closer to 0 than this. Here we have 0, we have plus, we have minus, showing our direction of approach. Then after 0, we're having 0.001, 0.01, 0.1. 1 over x gave us minus 10. That's for minus 0.1. Then for minus 0.01, that means as we go closer to 0, we're having minus 100. Then for this guy, we're having minus 1000. Okay, let's see what happens. Let's now come from the right. We have 10, we have 100, we have 1000. That means as we keep going closer, the value keeps increasing, tending to positive infinity. Whereas as we keep going closer from the left, the value keeps decreasing, tending towards negative infinity. So we can say that the left-hand limit, that means limit of 1 over x, as x approaches 0 minus is equal to negative infinity. Then limit of 1 over x as x approaches 0 plus is equal to infinity. You can see that the two limits are not equal because negative infinity is not the same thing as positive infinity. So we can say that this function has no limit as x tends to 0 because the condition says that these two must be equal for the function to have a limit. So the next thing we'll be talking about will be properties of limits. So the first property we have is if f of x is equal to k, where k is a number, that means this is a constant function. This is the graph. We'll have x, and here we'll have f of x, meaning that whatever x is, that f of x is equal to k. Then the limit of f of x will also be k as x approaches c. So you can say pick this point to be c. As x is approaching c, the answer is still k. Pick this point to be c. As x approaches c, the answer is still what? K. So the limit of the function of x as x approaches c will be k if f of x is k. That's a constant function. The second one, limit of f of x as x approaches c is equal to f of c. What this means is that wherever you have x in the function, replace x with c, and that gives you the limit. Then for the third one, we have limit of x to the power n as x approaches c. So you can see that here we say f of x as x approaches c is equal to f of c. So here we have f of x, and that's x to the power n. Put c where you have x, you'll be having c to the power n. Then for the fourth one, limit of f of x, that's the nth root of f of x as x approaches c is equal to the nth root of f of c. So replace x with c in the function, but if replacing it gives you something, let's say intermediate or whatever, and by other means you're able to calculate the limit. So we can now say nth root of L. But the condition is that L must be greater than 0, because whenever L is negative and n is even, the function will be undefined. But if n is odd, that means L can be negative or positive. But the moment n is even, L must be a positive value, that means must be greater than 0. Otherwise, the answer you got is undefined. Now, if the limit of f of x as x approaches c is equal to L, and limit of g of x, this is another function, as x approaches c is equal to n, then we'll come to number 5. The limit of f of x plus g of x as x approaches c is equal to L plus n. And the limit of f of x minus g of x as x approaches c is equal to L minus n. Now for the sixth one, limit of f of x times g of x as x approaches c is equal to Lm. Then for the seventh one, limit of f of x over g of x as x approaches c is equal to L over m. That is if n is not equal to 0. Else, your answer is undefined. That means you have to use another method to find the limit. And the eighth one, the limit of f of x squared, that means f of x times f of x as x approaches c is equal to L squared. Now let's take for instance f of x is equal to 2x plus 1 and g of x is equal to sine x over x. Now let's say x is approaching 0. So we know that the limit of this guy will be 2 into 0 plus 1, that is 1. And the limit of this guy will be cos 0 over 1, that gives us 1. So let's try the fifth property, f of x plus g of x or minus g of x. Let's see what happens. So adding the two functions, we have 2x plus 1 plus sin x over x. Now this is over 1. Taking the common denominator, we have x, then we're having 2x squared plus x plus sin x. Now, we said as x approaches 0. So we put 0 here, we're having 2 times 0 squared. That gives us 0 plus 0 plus sine 0, 0 over 0. This gives us 0 over 0. You can see that it is undefined. 0 over 0 is not a number. So what do? We differentiate the numerator and denominator. We'll be having 4x plus 1 plus cos x over 1. Differentiate this, you have 4x. Differentiate this, you have 1. Differentiate this, you have cos x. Differentiate this, you have 1. Now put 0. So we're having 4 into 0 plus 1 plus cos 0 over 1. This gives us 1 plus 1, which is equal to 2. So if we had said L plus M, as this property states, we would have gotten 2. This shows that this property is correct. Now let's try the one for multiplication. Let's say that f of x is equal to 5 and g of x is equal to sin x over x. The limit of this guy is 1. Then the limit of this guy is 5 because this is a constant function. So we'll say f of x times g of x. This gives us 5 times sin x over x. This gives us 5 sin x over x. So how do we get the limit? If you put x is equal to 0 and 0 here, you'll be having 0 over 0. So what do? Differentiate the numerator. You'll be having 5 cos x over 1. This gives us 5 times cos 0, which is equal to 5 times 1, which is equal to 5. So assuming we just multiply their limits, that's 1 and 5, we would have also gotten 5. So you can see that this property is correct. Let's try the one for division. So let's say we have f of x over g of x. This gives us 5 divided by sin x over x, which is equal to 5 times x over sin x, which is equal to 5x over sine x. Now substitute for x with 0. We're having 5 times 0 equal to 0, sine 0, 0. So you can see it's undefined. What do? Differentiate the numerator. Differentiate the denominator. That gives us 5 for the numerator and gives us cos x for the denominator. So substituting again, we have 5 over cos 0, which is 5 over 1, which is equal to 5. So we would have achieved this just by dividing 5 by 1, and that gives us what? 5. You can see that the seventh property is correct. So these are the properties of limits. The next thing we want to talk about, methods for calculating limits. There are 3 basic methods for calculating limits. The first one is the method of direct substitution. The second one is the method of factorization. And the third one is L'Hopital's rule. So what's direct substitution about? When you have x in the function, put c. That means limit of f of x as x approaches c is equal to f of c. Take for instance, you have limit of 2x plus 1 as x approaches 4 is equal to 2 into 4 plus 1, and that gives us 9. Now, for the method of factorization, what are we supposed to do? When you are asked to find the limit of a function as x approaches a particular point, and you realize that the method of direct substitution does not work, what do? Try cancelling common factors. The moment you cancel out common factors, substitute for x again and see if you would have the limit. So in this case, we have x squared minus 1 over x minus 1. If we put 1 here, we'll be having 1 squared minus 1 over 1 minus 1. And that gives us 0 over 0, which is undefined. What do? We factorize x squared minus 1. And that gives us x plus 1 into x minus 1. Then divided by x minus 1. So we'll cancel out x minus 1, x minus 1. And we are left with x plus 1. We'll substitute for x again. Then we'll have 1 plus 1, and that gives us 2. So that's for the method of factorization. Then where the method of factorization does not work, you can try L'Hopital's rule. But this method can only be applied when the limit of the original function gives us 0 over 0 or infinity over infinity. So when the limit of the original function gives us either of these, then what do? Differentiate the numerator, differentiate the denominator, try finding the limit. If you still can't get it, differentiate again. You keep differentiating until you are able to get the limit. So let's differentiate the numerator. We'll be having 2x. We differentiate the denominator, we'll be having 1. Then at 1, what do we have? 2 times 1. That gives us 2 into 1 over 1. That gives us 2. So you can see that we got 2 and we got 2. Now, the next one to look at is limit at infinity. So this is the symbol for infinity. So we are looking at positive infinity and also negative infinity. Now we have limit of 1 over x as x approaches infinity. What do we see? We have x, we have 1 over x. Now approaching positive infinity, we have 10, 1,000, 100,000. So what happens to 1 over x? Initially we have 0.1, then 0.001, then 0.00001. You can see that this value is greater than this value, and this value is greater than this value, meaning that this value is tending towards what? 0. So the function is tending towards 0 as x tends towards what? Infinity. Now let's look at the second one, limit of 1 over x as x tends towards negative infinity. So we're having x, then 1 over x. So we have minus 100,000, minus 1,000, minus 100, minus 10. So x is tending towards negative infinity. What does it mean? Decreasing without bound. Then for the other one, increasing without bound. So it's tending towards negative infinity because this is greater than this is greater than this is greater than this. So we are moving towards negative infinity. What happens to the function? You can still have minus 0.00001. Then for this one, have minus 0.001. For this, we have minus 0.01. And for this, we have minus 0.1. Now, remember that minus 0.1 is lesser than minus 0.01. And minus 0.01 is lesser than minus 0.001. And this is lesser than this, meaning that this is closer to 0 than this. This is closer to 0 than this. This is closer to 0 than this. So as we tend towards negative infinity, what do we see? That the function 1 over x tends to 0. So let's see how this is applied in calculating limits at infinity. Now let's say we want to calculate the limit of 1 over x squared as x tends to infinity. You will notice that the limit will also be 0, just as this one is equal to 0. The same thing applies to this. 1 over x cubed, take the limit as x approaches infinity, is also equal to 0. The only difference between the three is the rate at which it approaches 0. So why this will be approaching 0 faster than this? This will be approaching 0 faster than this. but all of them are tending to 0, which means that the limit of functions like this will give us what? 0. Now let's apply this knowledge here. We are asked to calculate the limit of 2x squared minus 2x plus 2 over 3x squared plus 4x minus 5 as x tends towards infinity. What do we do? Because if you take the limit of the numerator, take the limit of the denominator, you'll be having infinity over infinity. So how do we handle this to know what the limit is actually? We divide the numerator by x squared and divide the denominator by x squared. So we're having 2 minus 2 over x plus 2 over x squared divided by 3 plus 4 over x minus 5 over x squared. Now put infinity here, put infinity here, put infinity here, put infinity here. This will give us 0. This will give us 0. That's the limit at infinity. This will also give us 0. This will also give us 0. So we are left with 2 over 3. That means the limit of this function as x tends to infinity is equal to 2 over 3. We can achieve this using L'Hopital's rule. Let's try it using L'Hopital's rule. Differentiate the numerator. We'll be having 4x minus 2 over differentiate the denominator, we'll be having 6x plus 4. Now, if you insert infinity here, you'll still be having infinity over infinity. So what do? We differentiate it again. We'll be having 4 over 6 because when you differentiate this, you have 4, this 0, this 6, this 0. So you'll be having 4 over 6, and that gives us 2 over 3. So you can see that we got the same answer using L'Hopital's rule. Now let's take another example, 2x plus 5 over x squared minus 4x plus 2 as x tends to infinity. This guy will give us infinity, this guy will give us infinity. So how do we solve it? We go by the same method. Divide numerator and denominator by x squared. So you'll be having 2 over x plus 5 over x squared divided by 1 minus 4 over x plus 2 over x squared. Now take the limit as x approaches infinity. This gives you 0, this gives you 0, this gives you 0, and this gives you 0. So that means we're having 0 over 1, which is equal to 0. So you can see that the limit is equal to 0 as x tends to infinity. Using L'Hopital's rule, what do? Differentiate numerator, differentiate denominator. You'll be having 2 over 2x minus 4. You'll be having 2 over 2 into infinity minus 4. This will give you 0. So in case you're in doubt, infinity here means increasing without bound. So pick a number bigger than it. Pick another number bigger than it. So keep going, keep increasing without bound. You will see that the function will be decreasing, tending towards 0. But we can still differentiate again. To clarify, differentiate the numerator, you have 0. Differentiate the denominator, you have 2. 0 over 2, that gives us what? 0. So the limit of this function as x tends to infinity is equal to 0. Let's try another example. Now we have limit of 8x plus 4 over minus 4x plus 2 as x approaches infinity. Now what happens? As x approaches infinity, the numerator approaches infinity also. Then as s approaches infinity, the denominator approaches negative infinity. What does this mean? That the numerator increases without bound as x increases without bound. Then the denominator decreases without bound as x increases without bound. So let's say we have, for the first number, let's say we have minus 4 into 10 plus 2. Then for the second number, minus 4 into 100 plus 2. So you can see that we're increasing x. We can also say minus 4 into 1000 plus 2. This gives us 2 minus 40, that's minus 38. This gives us 2 minus 400, that is minus 398. This gives us 2 minus 4,000. That is minus 3998. So you can see that we are tending towards what? Negative infinity as x tends towards positive infinity. But for the numerator, you see that as x is increasing without bound, the numerator is increasing without bound, because if you have 10, 8 times 10 plus 4, that gives us 84. If you have 100, 8 times 100 plus 4, that gives you 804. If you have 1,000, 8 times 1,000 plus 4, that gives you 8,004. So you can see that the numerator is tending towards infinity, while the denominator is tending towards negative infinity. So how do we resolve the issue? Seeing that our answer is undefined, we apply limit at infinity. So we're having 8 plus 4 over x divided by minus 4 plus 2 over x. What I did, I divided numerator by x, divided numerator by x. Now put infinity here. We'll be having 8 plus 0 over minus 4 plus 0. This gives you 8 over minus 4, and this gives you minus 8 over 4. Now, using L'Hopital's rule, we'll be having differentiate the numerator, we'll have 8, differentiate the denominator, we'll be having minus 4, which is sent as minus 8 over 4, which is minus 2. This one is also minus 2. So that's what limit at infinity is about. Let's talk about infinite limits. That means limits without bound. Now, when the limit of a function increases or decreases without bound, as the function tends to a particular point, we say that the limit is infinite. So it's positive infinity if from both sides it tends to positive infinity, and negative infinity if from both sides it tends to negative infinity. So we have an example, limit of minus 4x plus 5 as x tends to infinity. What do we do? Pick a number, you can say minus 4 into 2 plus 5, minus 8 plus 5, which gives us minus 3. Then take another number, minus 4 into, increase it now, let's say 20 plus 5. We'll be having minus 80 plus 5, and this gives us minus 75. So pick another number, let's say 200 plus 5. What do you have? You are having minus 800 plus 5, which is equal to minus 795. So you can see that as x is tending towards infinity, this function is not tending towards a particular number. It is just decreasing, decreasing, and decreasing. Initially, we had minus 3. Now we're having minus 75. And now we're having minus 795. Repeat it again using a bigger value. You have a more negative value as the output. So in that case, we say that the function is tending towards what? Negative infinity. So the limit is equal to negative infinity. Let's see what happens to this one. 4x plus 5 as x tends to infinity. So we're having, let's say, 4 into 2 plus 5, then 4 into 20 plus 5, and 4 into 200 plus 5. This gives us 4 into 2, 8 plus 5, that's 13. Then this gives us 80 plus 5, 85. This gives us 800 plus 5, that is 805. So you can see that it's not tending towards a particular number. It is just increasing and increasing. In that case, the limit is infinite. So for this one, we had negative infinity. For this one, we had positive infinity. So that's what infinite limits is about. Let's look at this example. Limit of 1 over x squared as x tends towards 0. Now, tending towards 0 means that we must approach 0 from the left-hand side and from the right-hand side. So we have x, and we have 1 over x squared, minus 0.1, minus 0.01. Then at this point, we have 0, then 0.01, 0.1. Approaching from the left, we have 1 over 0.01. That gives us 100. Then for this guy, we're having 1 over 0.0001, and that gives us 10,000. Then let's approach from the right. We're having 100 for 0.1 and 10,000 for 0.01. So approaching from both sides, you can see that we are tending towards positive infinity. So in that case, we say that the limit of this guy is positive infinity. So that's what infinite limits is about. So before we talk about applications of limits, I want us to solve these problems. Here we have the limit of x squared plus x minus 2 over x squared plus 2x as x approaches negative 2. Now, when we put negative 2, that's using the method of direct substitution, we'll be having 4 minus 2 minus 2 over 4 minus 2, sorry, plus 2 into minus 2. And this will be giving us 4 minus 4 over 4 minus 4, which is equal to 0 over 0. So the limit of the function as x approaches minus 2 is undefined. What do? We try the method of factorization, and that gives us x squared plus x minus 2 over x into x plus 2, x plus 2 into x minus 1 over x into x plus 2. So we'll be having x plus 2 cancelling x plus 2. That gives us x minus 1 over x. Now let's put minus 2. We'll be having minus 2 minus 1 over minus 2. This gives us minus 3 over minus 2, which is equal to 3 over 2. So that's the limit of the function as x approaches negative 2. Now let's try this using L'Hopital's rule. Differentiate the numerator, you'll be having 2x plus 1. Then differentiate the denominator, you'll be having 2x plus 2. Now substitute for x, you'll be having 2 into minus 2 plus 1 over 2 into minus 2 plus 2. This gives us minus 4 plus 1 over minus 4 plus 2. And this gives us minus 3 over minus 2, which is equal to 3 over 2. So you can see that we found the limit of the function as x approaches minus 2 using L'Hopital's rule and factorization method. Let's solve for the next one. Here we have 1 minus cos x over x squared. Now let's check if we have intermediate as x approaches 0, because we want to know the limit as x approaches 0. We have 1 minus cos 0 over 0 squared. This gives us 1 minus 1 over 0, which is 0 over 0. So in that case, we can apply L'Hopital's rule. So what do? Differentiate the numerator, you have 0 minus, differentiate cos x, you have minus sin x. So in that case, plus sin x over, differentiate this, you have 2x. So we have sin x over 2x. X equal to 0, you'll be having 0 over 0, still intermediate. So what do? We differentiate again. Differentiate the numerator, you have cos x. Differentiate the denominator, you have 2. Now put 0 where you have x. You're having cos 0 over 2. And that gives us 1 over 2, which is equal to 0.5. So you can see that we've applied L'Hopital's rule. Let's go to the last thing we want to talk about in this lesson. That is application of limits. Now there are different applications of limits, but we just want to focus on differentiation because we can apply the concept of limits in differentiation. Now look at this. Differentiation, or finding the derivative of a function, whichever one, is taking the limit of the slope, that's change in y over change in x, as change in x approaches 0. That's what differentiation is, or finding the derivative of a function is. So it's equivalent to dy dx. So we have two functions here. The first one, y is equal to 2x plus 1. Normally, to differentiate a polynomial, what do? In the case of y is equal to 2x plus 1, we differentiate 1, we have 0. We differentiate 2x, we have 2. So dy dx is equal to 2. You notice that we'll get the same answer, that's 2, using this definition. Now already we have y is equal to 2x plus 1. Notice that when x changes, definitely y will also change. So y plus change in y is equal to 2 into x plus change in x plus 1. So we're having that y plus change in y is equal to 2x plus 2 change in x plus 1. Making change in y the subject, we have 2x plus 2 change in x plus 1 minus y. And this is the same thing as 2x plus 2 change in x plus 1 minus 2x minus 1. Remember that y is equal to 2x plus 1. So this will eliminate this, and this will eliminate this. So it means that change in y is equal to 2 change in x. We are looking for change in y over change in x. So change in y over change in x is equal to 2. Take the limit of a constant function. The limit of change in y over change in x as change in x tends to 0. This is a constant function. That means the limit as we tend to 0 will also give us 2 according to the properties of limits. Let's try the second one. We have y equal to 3x squared plus 5. So change in y plus y is equal to 3 into x plus change in x squared plus 5. We'll be having change in y plus y equal to 3 into x plus change in x into x plus change in x plus 5. So we'll be having 3 into x times x, x squared, x times change in x, that's x change in x times change in x, that's x change in x plus 2x change in x. Then we'll be having plus change in x squared, then plus 5. Multiply everything in this bracket by 3. We'll be having 3x squared plus 6x change in x plus 3 change in x squared plus 5. Now make change in y the subject. We'll be having that change in y is equal to this minus y. And remember that y is 3x squared plus 5. So we'll be subtracting 3x squared plus 5 from this equation. This is 3x squared and this is 5. So change in y is equal to 6x change in x plus 3 change in x squared. Now we are looking for change in y over change in x. That's the function we are looking for. So we're having that change in y over change in x is equal to 6x plus 3 change in x. Now let's take the limit. As change in x tends to 0, what happens? We'll substitute for change in x in this equation. That means where we have change in x, we'll put 0. So we'll be having that limit of change in y over change in x as change in x tends to 0 is equal to 6x plus 3 into 0. That gives us 6x. And that is the derivative of this function. Remember, if you differentiate 5, you have 0. And if you differentiate 3x squared, 2 times 3 is 6. And that gives us 6x. So we've come to the end of the lesson. I believe you enjoyed it and you've had a better understanding of the concept of limits. Thank you for watching. Please comment, like, share, and subscribe. Please do well to subscribe. Your subscription is very, very, very important to me. You can also check my previous videos. I've done 3 videos on function, introduction to function, the domain and range of a function, types, compositions, and inverse of a function. Once again, thank you so much.